video demonstrates the Key Exchange and Management System tool, or KEMS tool. This tool is designed to generate symmetric keys for a set of pre-registered clients. These clients are registered through a SELFY PKI. In server mode, two or more KEMS clients want to securely exchange data. To obtain a common key, they will interact with the KEMS server that will generate a key, store it, and share it with the authorized clients. The clients and the server have a certificate that was generated in a SELFY PKI. This process is as follows. A primary client, which is the one creating the key, has to send a request to the server with the parameters for the key it wants to generate. The server generates the key and stores it, encrypted in a local database. Hence, if the server was compromised by an attacker, the attacker would not get access to the keys stored in the database. When another client, that we will call secondary client, wants to obtain the key to communicate with the primary client, it also has to send a request to the server with the parameters of the key it needs. If no such key exists, or if the client is not authorized to get this key, the server returns an error code. Otherwise, the keys return encrypted. Then, both clients have to exchange the required information to decrypt the key, which can then be used to decrypt shared data. The key is exchanged through a secured connection using OpenSSL and OpenQuantumSafe for post-quantum algorithm. When the key is no longer needed, the primary client requests its deletion by the KEMS server. If the client is authorized to delete the key, the KEMS server removes the key from its database. For this demonstration, we have three shell windows. The KEMS server is on the left window. The primary client is on the top right window, and the secondary client is on the bottom right window. First, as we saw previously, the primary client requests the creation of a new key to the KEMS server. We can see that the key generated is the same as the one that has obtained the KEMS client, but it was sent encrypted. Then the primary client will generate an encrypted string of characters. So here we have the clear data, my super secret data, and the result encrypted with the key received. If another client wants to get the same key, it has to send a GET request to the server. It will receive the key encrypted and also the associated salt. The secondary client then has to get the necessary data from the primary client to decrypt the key. We can see that the secondary client obtained the same key as the primary client. It will now be able to decrypt the encrypted data. And we obtain the same clear data as the primary client. Then, because the key is no longer needed, the primary client will send a request to delete the key on the KEMS server. Because the primary client is the client that created the key is deleted by the server. Using the KEMS server, two or more clients can therefore obtain a securely generated key to securely exchange data. This video demonstrates the Key Exchange and Management System tool, or KEMS tool, in client mode. In this situation, the clients want to exchange data without establishing a connection to the KEMS server. Both clients still have a certificate provided by a SELFY PKI. To work in client mode, both clients first have to negotiate a shared key. This step is accomplished using OpenSSL and post-quantum algorithm and will be demonstrated between the Remote Attestation System verifier and the Remote Attestation System prover. When the communication is established, both clients can securely exchange data using this secure channel. Once the communication is over, the key is deleted. If the clients want to exchange data again, the negotiation must happen again. To demonstrate the KEMS in client mode, we use the Remote Attestation System. The Remote Attestation System is already running, and we have here the netcat shell that is used to receive the attestation result. That would be a VSOC in a real-world scenario. And here we have a curl request that will trigger the attestation. The collector is already running. This is the part that is collecting events from the execution of an application. We can also check that there is a network capture running on the local interface, and currently there are no packets on this interface. If we run the curl request, we see that it is sent and that we obtained some results with a state 1, so the attestation succeeded. More details of the Remote Attestation System can be found in its own demonstrator video. We can also see that the collector did receive the request and quoted some results. If we look at the network capture, specifically the client hello and server hello, we can see in the details of the TLS protocol that the key exchange mechanism is using Kyber. Both these versions of Kyber are post-quantum algorithm. Furthermore, we can also see in the certificate used by the verifier that this certificate is signed using dilithium 3, which is also a post-quantum algorithm. In this scenario, we can therefore see that our clients, the verifier and the prover, can exchange attestation data securely through the network without the need for the KEMS server using post-quantum algorithms such as Kyber or dilithium.